everybody. Today we're going to start covering section 2.1 today. We'll also get into 2.2 as well. So today we're going to start talking about the scientific method. A lot of this is going to be review from things that you have already seen in biology last year or in other science classes. So let's just start off with kind of the basics. What is the scientific method? It is a logical approach of solving problems by observing and collecting data, formulating hypotheses, testing hypotheses, and formulating theories that are supported by data. So the scientific method you do every single day. It doesn't matter whether it's something as simple as you lose your phone and you make an observation. You see that you don't have your phone. You then start collecting data of where would my phone be? Could be in the living room, could be in the kitchen, could be in my bedroom. You formulate a hypothesis. I believe my phone is in the living room because that's where the last place I was. You test that hypothesis by going to the living room to see if your phone is see if your phone is there, and then you formulate your idea of either yes, it is, or no. Then you have to support that data by saying yes, my phone was in the living room, or no, my phone was not. So the first thing is an observation. So these are using your senses to obtain information. So a lot of times we use observations every day. So a simple observation, if you look around my classroom, I have two walls that are green, I have two walls that are white. I have an American flag, I have my name up on my wall, I have a graduation cap. There's all kinds of things you notice throughout the day. And it also involves making measurements and collecting data. So anytime you measure something, you're also making an observation of, oh, I noticed this is 3 milliliters or 3 centimeters or 25 meters, whatever it needs to be. There are two types of data. There's qualitative data and quantitative data. Qualitative data is describing. So a lot of times in chemistry, when we're using qualitative data, we're describing what it looks like or basically what it looks like or what it feels like. So smooth, rough, green, its appearance. I think of qualitative, the easy way to remember between the two. Qualitative is like the quality of something. So if you grab onto a shirt and you touch it, you're like, oh, it's really soft, or oh, it's green. So whatever that kind of describing attitude would be, that would be a qualitative data. Quantitative is dealing with numbers. So 2 centimeters, 3 yards, 3 milliliters, 25 grams, anything that deals with a number is going to be quantitative. So quantitative, an easy way to remember between these two, quantitative has an N in it. That N stands for numbers. So qualitative is the quality of something. Quantitative, with that N there, is the number. So an actual numerical number. So oftentimes we deal with systems. It's a specific portion of matter in a given region of space that has been selected for study during an experiment or an observation. So basically a system is where is this experiment taking place? Or where is this observation being taken place? So when you observe a reaction in a test tube, the test tube is the system. The test tube is where the reaction is occurring. So similar to our last example of the scientific method with your cell phone, that would be probably your house of, everything that I have is in my house, and that's where I'm conducting my experiment. So we were talking about our observations of the room. My classroom would be our system, because that's what we were describing and what we were talking about. Our second part of the scientific method is a hypothesis. So a hypothesis is scientists use generalized data to formulate a testable statement. Most of the time you'll hear a hypothesis be described as an educated guess. It's really just, you're taking a shot in the dark and you're going to try your best to explain why you think something is happening. A good hypothesis explains what you think will happen and why. It's not just as simple of, I think you'll need 25 milliliters of water to make this reaction occur. It's more of a, I believe you will need 25 milliliters of water because of previous data given and other experiments have proven 25 milliliters is the best form for whatever experiment you're dealing with. So being able to explain why you think it's going to happen and how is super important in the hypothesis. Hopefully you remember these from last year in biology, but we have different variables. A variable is any condition that cannot control or allow to change. So a variable is just basically part of the experiment. So what's going on? So we have the independent variable and the dependent variable. The independent variable is what is being changed in the experiment. When we do experiments, we always do a control group and an experimental group. The experimental group has this independent variable, something that we changed to it. So if I split this classroom in half, and half the class I taught as normal, and the other half of the class is I played rock music during the entire lecture and during labs and everything, and even during the test, I played super loud rock music. My independent variable would be the rock music, because that's the difference between the two. And let's say my hypothesis was, I believe that playing rock music will increase test scores by 20%. My dependent variable is what happened because of the independent. So the dependent is dependent upon the independent. So basically what changed, or what happened because of the change. So my dependent for that experiment would be test scores rising by 20%. So what are those test scores going to look like? That's going to be my dependent. Again, independent, what did I change in the experiment compared to the experiment and the control? So the rock music. The dependent, what happened because of it? And we have to look at the test scores. Did the test scores go up or down? We also need to know the difference between repetition and replication. So repetition is the expectation that an experiment will give the same result when it's performed under the same conditions. So I should be able to pursue the same experiment. So splitting the class in half and doing my rock music to every single one of my chemistry classes. I should be able to do that, no problem. That is repetition. Replication is the idea that experiments should be reproduced by other scientists. So I should be able to hand this off to Mr. Engelkamp or Mr. Hittrick or Ms. Holm or Mr. O and say, here, you do this experiment in your classroom and see what happens. So other scientists need or should be able to do the same test as you and get similar results. So it shouldn't be anything dramatically different between the two. It should be about the same. Are they going to be perfect? No, but they should be close. That's why scientists give specific instructions on how to do the experiment. So if I were to do this, I would have to give very specific instructions of the volume needs to be at 20, here's the type of music you need to be playing, here's how long it needs to be playing, here is the songs I played on this day. I would have to give very, very specific instructions. So that's why making recipes are so specific on heat, specific mixtures, and ingredients. Same thing when we're cooking. You have to give specific instructions. You've probably heard or talked to your grandparents and said, how do you make this? And they're like, oh, it's a dash of this or a pinch of this. And you're like, how big is a dash? How big is a pinch? What's a splash look like? And you're like, I have no idea. It doesn't make for replication very easily. But if they said you need a cup of milk and 3/4 cup of flour, you can do that and not have any problems, and you can easily replicate that recipe. Then we have the difference between a theory and a model. So a theory is a broad generalization that explains a body of facts and phenomena. A hypothesis that has been tested multiple times by different scientists. So anytime you hear a theory of something, it's a broad generalization. So we're like, in general, this is why it's happening. It's not quite to the law point where we're like, yes, every single time it's going to happen, but in general, yes, we're going to be seeing this something come true. And it's all because that hypothesis has been tested over and over and over again. It's been replicated over and over and over again. It's been repeated over and over and over again. When we get to that theory part, we're able to make a model. So an explanation of how phenomena occur and how data or events are related. And it's not always a physical model. Most of the time when we think of a model, we think of something physical. If you look at my classroom, I have models of the sun and the earth to show eclipses and things like that and how the phases of the moon. It doesn't always have to be physical. A model could simply be a graph or a chart that shows and explains why something is occurring. It doesn't always have to be a physical model in front of you. So we have the scientific method, something you've probably seen before, or hopefully have. First, you make an observation. You see something happening. You also make an inference based off prior knowledge to create a hypothesis as to why you think this is happening. You then go into the experimental side, and you're like, okay, why is this going on? Let's form an experiment. Then we're going to collect and analyze that data. Then we will draw our conclusion, and then repeat. Either yes, our hypothesis was true, and we want to redo it and see why, or no, it's not true, and we need to fix it with adjustments of maybe another observation of, oh, I missed this the first time. Let's try this now, so I can adjust my hypothesis and continue this over and over and over again. So the scientific method is more of a process and less of a step-by-step manual. It's something you're constantly changing over time. So that's section 2.1, that's just the scientific method. There is a video at the beginning, so if you want to go in, it's on the slides. It's the very first, like the third slide in. You can go ahead and watch that video as well. Just again, explains the scientific method. Today, we're also going to go into section 2.2, which is units of measurement. So the first thing is you got to know, what is a quantity? So measurements contain both the quantity, something has magnitude, size, or amount, and a unit. So basically, we have to measure it and get some amount to it, and then we can throw on a unit to explain amount of what. So a quantity is something that has magnitude, size, or an amount. So for example, a measurement in a teaspoon is the quantity is a volume. So how much space is being taken up. Same thing with when we're measuring in grams. We're measuring the mass of something, how much matter is in that object. So the quantity would be the number part, 2.3. So it has 2.3 amount of whatever. Then your unit has to be behind it, because that explains what type of quantity is it. Is it a volume? Is it a mass? We need to know those things because there's a big difference between 2.3 milliliters or liters or grams or kilograms. We have to know exactly what we're measuring and what we're dealing with at any time. So we deal with something called an SI unit. SI is a single measurement system called Le Système International des Unités. It's basically French. It's used to keep measurements consistent across the world. So any scientist will use SI units. It was adapted in the 1960s, so not that long ago. It's composed of 7 base units. All other units are derived by those 7. The bases are of the metric system, so they're always a power of 10. The metric system is much easier than what we use here in the States. So that's why, and plus it's just easier, everybody else uses it, so we can just kind of share all of our information between us and the rest of the world quite easily. We also use prefixes are added to the base units to indicate larger or smaller quantities. So instead of coming up with different forms of a unit, we're able just to add a prefix, and that tells us whether that number is really large or if that number is very, very, very small. Okay, so these are our base units. Our base units are length. I would make sure you fill these in on your chart in your packet. So for length, we always draw these in cursive, so this will be a cursive L is representative length. We always measure it in liters, and the unit abbreviation is a lowercase m. That is very important. So make sure you always have those unit abbreviations in there for you to have. Mass is our m, so anytime it's in a formula, you'll see m. Its unit name is grams. We always have a lowercase g. Time is a lowercase t, so oftentimes you'll see it drawn something like that. It's always measured in seconds, so not minutes, not hours, always seconds. And it's always represented by a lowercase s, or you could have SEC, just depending on who you're dealing with. Temperature is a capital T. That's why we need to be able to denote these. Temperature and time are 2 very different things. The big change is now we're in Kelvin. So science loves to use Kelvin. We'll talk more about it later. But it's represented by a capital K. And then the amount of a substance is a lowercase n, and that is a mole. We will talk more about moles. You'll get tired of moles as the year goes on. The abbreviation is MOL. You will have to have that written out. It is MOL because there is a difference between a mole and a meter. We don't have to worry about these last two, electric current and the luminous intensity. That is more of a physics thing, but our book has it in there. These are the main ones you'll need to know. So length, mass, time, temperature, and amount are the important ones. So make sure you have these copied down in your notes. Okay, the prefixes. So prefixes, I always like to start with the base. So this would be your liters, meters, grams, things like that. Moles, actually just be grams. Stop there. So meters, liters, grams are kind of your main ones for your base. So this is your base unit. And then if we are going to go to a larger number, so base of 10, we will go to deca. So D-E-K-A. So we can have a decagram, a decameter, a decaliter. So that would be represented by dA, and is to the first power. If we want to go to an even larger number, so 100 base, it'd be a hecto. So we have it represented by an H. So it'd be a hecagram, a hecaliter, hecameter, liter. That goes to the second power, base of 100. And then we have kilo. Kilo is our most common. It's represented by a K. So when you see kilogram, kg, or kg, that's what it's talking about. So a kilogram, which is to the third power, that is 1,000. We don't really get into mega, giga, or tetra. Those are more physics sort of things. We generally just stick within these three. So deca, hecto, kilo. Then if we're going to get smaller than the base. So we have deci. So we have a decimeter, a deciliter, a decigram. That is -1. So that's 1/10 of a base. Centi with a lowercase c. That is -2 power. It's 1/100th of a base. So a centimeter, a centigram, a centiliter. Then we also have milli, lowercase m. So it's to the -3rd power. And that's 1/1000th of a base. So that is a milligram, millimeter, milliliter. We'll oftentimes deal with milli as well. So the popular ones are kilo, milli, and then we stick to our base. Sometimes you'll see centi as well. We don't generally get any smaller than that, but the smaller one is micro, and it does get even smaller than that. Micro is represented by this like funky looking U here. It's 10 to the -6th, and that's 1/1,000,000th of a base. So a way to remember this, because you will need to know how to use this, is by a little acronym or a little saying. I say King Henry died. I call this, we have our base. So King Henry died, base, so we skip it, drinking chocolate milk. To me, that's the easiest way to remember it. You can also write it out. So King Henry died. Then we'll have our base here. Drinking chocolate milk. So this will help you be able to convert between milli to deca, hecto to base. Whatever it is, it makes it pretty easy to switch in between. So King Henry doesn't drink chocolate milk or die drinking chocolate milk. Either way works. So if you have any questions on that, let me know. I will have that written up on the board for a while, just until we get used to converting within our prefixes. All right, prefixes. So the prefix abbreviation is added in front of the base unit. abbreviation. So for cm would be a centimeter, kg, kilogram, ml, milliliter, hs is a hectosecond, dg, a decigram, dag or capital DG is a decagram. So if you wanted to go back to your chart here, you can change this to DA or to a capital D. Either way is correct. Either way will be fine with B. Whatever you prefer. Oftentimes, I'll just use a capital D just because it's a little bit easier. Okay, so real quick, so how many grams are in a kilogram? All right, so we have to look. We have our prefix kilo. A kilo, if we go back to our center here, kilo falls within this 1,000. So for every one base, there are 1,000 kilos. So that means there would be 1,000 grams. So your answer should have been A. So for every 1 gram, there are 1,000 kilograms, or there's 1,000 grams in a kilogram. Okay, we also need to talk about the difference between mass and weight. So oftentimes you'll hear, especially when we were practicing with the scales the other day, people are like, oh, the weight is this using our digital scale. When we use a digital scale, we're actually talking about the mass, not the weight. So the mass is the amount of matter in an object. That's what we measure in grams. So when we were messing around with the scales, or we had them out, we measure it in grams. So we're measuring the mass. Weight is the measure of force of gravity on an object. So when we take the mass of take the weight of ourselves, we're really looking at gravity pushing down on top of us, and that's going to tell us how much we weigh. But our weight can change depending on where we're at. So how does your mass on Earth relate to your mass on the moon? Well, if we think about it, you on Earth, you are made up of a certain amount of mass. You're made up of whatever you make up. Mass is the amount of matter in an object. What I'm made up of doesn't change when I go from here on Earth up to the moon. So I'm not going to change my mass. So my mass will stay the same. My weight, though, the moon doesn't have any gravity on it. So my weight is going to completely change based on what it is on here on Earth to what it is on the moon. So weight will change because the force of gravity, depending on where you're at, will dictate your weight. Your mass will not change. Your mass stays the same no matter what. Okay, so these are some derived units that you will need to know. The main ones are these bolded ones right here. So for example, volume, density, and then molar mass. You will solve for molar mass several times this year, so this is something to get used to. So volume, represented by a capital V, is shown in cubic meters, cubic centimeters, or milliliters. Generally, we're going to see it in this cubic centimeters and milliliters. The derivation is length times width times height. Oftentimes, you'll see it represented in letters, so length times width times height is going to give you the volume. So how much of a area is it taking up? Density is kilograms per cubic meter or grams per milliliter. So we have kg/m to cubed or grams per milliliter. Most of the time we're going to stick to that grams per milliliter. So that one is mass divided by volume. So you'll see it as a lowercase m divided by a capital V. We're going to work more with some density in this chapter starting tomorrow. So something we'll get used to. And then we also have molar mass. Molar mass is represented by a capital M. I generally show it by 2 capital M's. So molar mass. It's kilograms per mole or grams per mole. Oftentimes we'll just deal with it in grams per mole just to make our lives a little bit easier. And it's mass divided by amount. So M divided by N. mass divided by amount. We won't really have to worry about molar volume or energy. Something we won't really deal with. Those are energy and area. Those are both more of a physics thing, but they are there to write down if you need to. These are the three you will need to know, especially. So volume is the amount of space occupied by an object. So basically, how much space are you taking up? The SI unit is meters cubed, but centimeters cubed is more commonly used just because a meter is really large. When measuring a liquid or gases, scientists will use a non-SI unit like liters or milliliters. So technically, liters is not an SI unit, but it is very commonly used widely across the board, so we use it quite frequently. This you may want to know. 1 centimeter cubed equals 1 milliliter, especially when we get to converting. Sometimes they're given to you in centimeters cubed and they want it converted into milliliters. So it's good to know it's just a 1-to-1 ratio. So for every centimeters cubed is 1 milliliter. So make sure you have that written down in your notes so you have it. Density. Density is a ratio of mass to volume. So density equals mass divided by volume, or M divided by V. The SI unit is kilograms per meters cubed. It's commonly used as grams per centimeters cubed or grams per milliliter. Again, it just depends on what we're measuring in and what we're dealing with. If we're measuring something as a length, we'll use centimeters. If we're dealing more with like a liquid, it's going to be in milliliters. As the mass of a substance increases, the volume increases proportionately. So as the mass gets larger, the volume gets larger. Again, volume is just how much space it takes up. So that kind of explains itself as to it's not really going to change at all. They go up together. Often used to help identify a substance. So we will talk about how density, we can use it to help us figure out what type of substance we have and what we're dealing with. And varies with temperature, usually decreases with an increase in temperature. So if we have a certain density, oftentimes things will start to boil, and then when they boil, they start losing their mass. So their mass fluctuates, so that's going to dictate that change. I would write this down. I call this the density triangle. This is very helpful to help us solve for density problems that we will do tomorrow. So it's mass on top, draw a line down the middle. We have density and volume. And we draw it in a triangle. So when we're solving for these problems, depending on what we're dealing with, we can cover up what we're looking for. So if we need to solve for density, we cover up the D, and we get mass divided by volume. Mass divided by volume. Let's say we're looking for a mass, and they give us density and volume. We can cover up mass. If they're next to each other, you multiply. If they're on top of each other, you divide. So we have density times volume. Or the other way around, if we have a volume and a mass and a density, we can cover up volume and we get mass divided by density. So this is kind of helpful. A lot of kids like it. I highly recommend writing that down on your periodic table, on your notes so you have it. I will give you a sheet that gives you this on any test that we have so that you have it with you at all times. And it is up on your slides, so if you need to, copy it down. We already talked about it. Okay, so we're going to stop there. So make sure you're filling in your notes. I'm also going to have an extra credit assignment for you as well. So this is probably going to take you a little bit of time to sit there, go through your notes, but take your time. If you have any questions, please shoot me an email, and I will try and get back to you as soon as I can. Have a great rest of your day.